Hi, I'm Alex Alvarez and welcome to Dynamics 6. In this tip we're going to be talking about goals, and goals are a way to design particle motion so that they are attracted to either a transform node or to the UV coordinate space of a NURB surface. And any particle object in Maya can have more than one goal. So being able to use this technique allows you to attract particles and get particles, so let's say, flow along a surface, so that if you're trying to do something like getting a character to sweat, you could do that by having particles flow along the U or V coordinate space. Or if you're trying to get a character that's made out of dust or made out of sand, and you're trying to get that character to be blown away, or a logo or whatnot, again, goals can be used for those kind of effects. It's really very flexible, and you can still use all the regular particle tools such as fields to design your particles, and using all of them together can yield some pretty complicated and interesting effects. So that's what we'll be talking about. So to begin talking about goals, what I'm looking at in here is a Omni emitter. And this emitter is emitting into a single particle object. The particle object does not have any fields connected to it right now. And all of the attributes on the particle object, except for its render attributes, are at the default. So that if I select the particle object, we'll see that its conserve is at 1. Conserve is conserve momentum, and it's a very, very important attribute, as it makes a very big difference on how particles behave. So that's at the default value right now. So to create a goal for these particles, a goal can be either a transform node, a piece of geometry, either poly or NURBS, or it can be another particle object. And goal literally means what its name implies, meaning that the particles target something else in the scene, and they move towards that object. And then each particle will have something called a goal weight that'll determine how much it's attracted to that object. And so there are a lot of different things you can do with that basic premise of what goals are. So to explain them, what we're going to do is start with the simplest thing, which is using a transform node as a goal, and then we'll move into using geometry or particles. So for a transform node goal, any object in Maya that you can pick, move, rotate, and scale has a transform node, whether it's a light or a camera or a piece of geometry or whatever. So any of those types of transform nodes can be set to be a goal for particles, and what that's going to do is the particles are going to move towards the pivot point of that transform node. And particles can have multiple goals. So a single particle object can be attracted to multiple transform nodes or multiple pieces of geometry. So let me create a transform node for these particles to become attracted to. Again, I could create any piece of geometry or a primitive or whatever, but I'm just going to create a locator. And a locator has a transform node. I'm going to move it to the upper left. And so now we can see this locator sitting up here. To get the particles to see that locator as a goal, what I'm going to need to do is first select the particles and then shift select the locator. And with these objects picked, what we're going to want to do is go in Dynamics mode to the Particles pull-down menu, and in here there is an item called Goal. And if we go to the Creation dialog box for that, what we'll see, if I hit Reset, is there are not very many options. It's a very, very simple dialog box. And the options that you have are either Goal Weight or Use Transform as Goal, which is a checkbox. So what I'm going to do is I'm going to leave the goal weight at the default value, which is 0.5. And then this little item underneath that says Use Transform as Goal, I'm going to turn that on so that it uses the pivot as the goal, or the pivot point for that object. So if I had a piece of geometry, we'll see that this is going to make a big difference, that checkbox. For the locator, it won't. I'll hit Create. And if I go back to frame 1, first I'm going to select the particle object. Or look at the outliner. In the outliner you can see that nothing new was created. No new node or anything like that was created in the outliner to represent our goal. But if you select the particle object, what you will see is something new will appear in here. Specifically, it's now going to have something called goal weight in the channel box. And if I open up the attribute editor for my particle object, you will see that there is a folder in here. Let me just close all the default ones that are open. There's a folder called Goal Weights and Objects. And if I open that up, you will see that it also is listing something in here, where it says Goal Smoothness, then Locator 1, and then Goal Active. And so basically, for each goal that you add to a particle object, in this folder in the attribute editor for the particle shape node, you will be able to see all the objects that are goals for the particle, their weight values for each object, and then whether each one is on, and then also this smoothness, which we're going to need to talk about. But before we go and change anything, let's hit play and see what happens. So all of a sudden, our particles are behaving very differently in the sense that, you can see we have streak mode particles, meaning that they're going to, sort of streak themselves out based on what direction they're moving in. And you can see that those particles are clearly moving to where that locator is. So let's go real quick and take this locator and set some keys on it so it's moving. So I'm just going to get this locator to move, let's say, left and right over a few frames, so that we'll be able to see that it really is that locator and its position that are attracting the particles. So if I hit play now, we're going to see this. So notice how those particles are moving to where that locator is, as that locator moves from side to side. Well, if we then go in and select the particle object, let's start working with some of these attributes to see why things are doing what they're doing. First of all, when you look at this, you might think that you could probably do a very similar thing using a radial field that has a negative magnitude, and that's true. But there's certain things that are convenient about using a locator as opposed to using something like a field, and then once we get into geometry, the behavior will be completely unique. So the first thing to point out as far as why the particles are behaving the way they are, it's related to a few attributes that are on the particle object. The first thing is this particle does have a conserve attribute. Conserve means conserve momentum, and so what we're looking at here is that the particles are flying towards the locator. They're shooting past the locator and then coming back towards it, because when they conserve momentum, they tend to have an oscillating motion. If I set the conserve to 0 on my particle object, all of a sudden we'll see this, in the sense that those particles do not conserve momentum now, so that they just move towards the locator, but they do not fly past the locator. They'll just get attracted to it and then eventually stop right when they hit it. So you can see how big of a difference conserve has. So when you're using goals, and we're going to change the conserve in a few different cases, when you want to remove or get rid of that oscillating motion, or you want to diminish it, just lower your conserve. So again, if let's say I put it to a value of 1, we can see how those particles shoot past and then just sort of orbit around that locator until they eventually will slow down. Well, if I put the conserve to 0.75, go back to frame 1, we can see this difference in behavior. As far as now they lose energy, but they still have a little bit of oscillation. Then in here, if we move down a little bit, we have our goal smoothness attribute, as well as our goal weight attributes, and then the goal active. The goal active attribute is a Boolean. It's either on or off. That's pretty obvious what that does. If I turn goal active to 0 for off, what we'll see is that that goal no longer has an effect. And so they're no longer being attracted to that goal. So let's turn that back on. Okay. Then in here we have the goal weight and goal smoothness. Goal weight is how the particles, or how much the particles are attracted to that goal. The values in there will go from 0 to 1. If I enter a value of 0, it's going to be basically like turning the goal weight off. And so now you can see they're no longer attracted. If I enter a value of 1, what we're going to see in here is that those particles just get completely locked onto that locator. You don't really see so much of a movement towards it. They just sort of snap onto it. With a goal weight of 0.9, 0.8, we can start to see how as we lower that goal weight, it increases how long it takes for the particles to reach the locator. So if I entered a goal weight of 0.1, what we're going to see is those particles are going to slowly move towards that locator. Let's put in a value of 0.2. So the default goal weight value of 0.5 in the dialog box is something that very often you're either going to increase or decrease or even animate as you determine how you want these particles to behave in your scene. And so you can see for a case like this where we just have a single locator that's a goal, by lowering the conserve and lowering the goal weight, we get a much smoother result where you can see that these locators could be used to design, let's say you have like a laser beam that's supposed to be shooting something. Well, that locator could be parent to the object that the laser blast is supposed to be aiming at, and therefore we'd be able to see
how we could control where the blast hits in the scene by just parenting that locator to something. Then we have this attribute called goal smoothness. Goal smoothness determines how the goal weight value influences the attraction of the particles to the goal. The easiest way to understand it is really to just look at this image, which basically is showing you that how goal weight versus goal smoothness create a relation. By default, the goal smoothness has a value of 3. And so that's what we're looking at in this middle curve right here. So that as the goal weight goes from 0 to a value of 1, you get this smooth curve that determines it. When you put the goal weight to a value of 1, you get this curve on the left, which is linear, which very often I find to be the most intuitive, meaning that I get a linear relationship as far as how the particles get attracted to their goals, so that it's really how I keyframe the goal weight that can determine bell curves or different types of curves in here. So that if I keyframed my goal weight with a spline key versus a flat keyframe, I could have a more intuitive control over this. And if we go back out here, right now we have, let's say, a goal smoothness of 3. If I enter a goal smoothness of 1, notice how it completely changes the attraction, in the sense that now a goal weight of 0.2 is more like what we had before when we had a goal weight of 0.6. So it's really up to you to determine whether you choose to change the goal smoothness at all or not. If you're going to be animating your goal weight, it can be a useful thing to change, although you usually wouldn't keyframe your goal smoothness. You would just choose a value based on the kind of curve relationship you want. So now that we can see this single locator is behaving as a goal, what I want to do now is I'm going to delete the animation on that locator so that the locator is no longer moving, so that I'm back to having something like this. And I'm now going to create another locator. And this locator, let's put in the upper right. That's called locator 2. Well, now I'm going to select my particle object, select this new locator, and go back to the goal creation dialog box, use transform as goal, and hit create. What we will now see is I'm going to select these locators, or rather the particle object, go to the attribute editor, and in our goal weight and object folder, you will see now it lists both locators. We still only have a single goal smoothness attribute, but you will have a goal weight value for both of the locators. So however many constraints, or not constraints, goals you start adding to your particle object, you'll get a long list in here so that you can go and use these little sliders to determine your weight values. Well, I'm going to enter both of them so that both locators have a goal weight of 0.5. And let's go back to frame 1 and hit play. You'll see this. So when you have multiple goals, your particle object is going to average the position between those two goal objects. But something that you could do is keyframe those weight values or write expressions on them or whatever you want to do, so that your particles can be attracted to one locator for a certain period of time, and then maybe the goal weight can fade off for that locator and fade on for another one. If we wanted to do something like that, let's say I go and switch to flat keys, and I keyframe these goal weight attributes in the channel box. So what I'll do is I'll set things up so that the locator on the left has a high goal weight at frame 1, a value of 0.5, and the locator on the right will have a goal weight of 0 at frame 1. If I keyframe these, if I hit play, we'll see this. But as you'd expect, if I go to frame 60 and then swap those values in there so that the one on the right has a higher goal weight, and I set another key and I hit play, what we're going to see is this. And so notice how as the goal weight is animated from 0 to 0.5, the relationship that we're getting as far as how those particles switch which locator they're attracted to. If the goal smoothness was set to a value of 1, we're going to get more of a linear transfer. So notice that as the smoothness, or again, with the smoothness set to 1, we get a linear relationship as the goal weight is animated, so that when we hit play, we're seeing how those particles evenly, as far as their speed, transfer from one locator to the other. But when the goal smoothness has a value of 3, and we play this back, notice how it's really in the middle there of animating the goal weight value that we get the biggest amount of speed up. So if you, again, using, let's say, like the laser blast example, like one locator could be parented to one character in the scene, and the other locator could be parented to another character in the scene, and you could be animating the goal weights to determine how some laser switches from one object to another, or one character to another as far as what its target is. Simple example that should give you an idea of how something like this can be done. Also, by using these transforms, if you strategically placed your transforms on your particle object and animated the goal weights as the particles got near the locators, you could use that as a way to create sort of like a motion path for your particles. Although Maya already has something called the curve flow effect, which sets something up like that for you and writes all the expressions you would need for that to work intuitively. Basically meaning that you could have, if I went into the front window, you could create several locators. So let's say we have one, and then create another one, and create another one. So that looking at these three locators, we could animate the weights so that the particles first go to this locator, then move to this locator, then move to the third locator to get them to, let's say, move on an arc that's defined the way we want. But again, using the curve flow effect or some other techniques involving goals can be easier than doing it that way, and this will make sense as we move on to using geometry as goals. So at this point, this is the basics of how goals work, in the sense that you have a goal weight value and you can have as many goals as you want. And so at this point, we just have the two. So if we want to see another example of, let's say, using a locator as a goal, I'm just going to open up a scene which has, let's say, this laser that's going to be shot towards this pole back there. So if I hit play, we're going to see that these particles are being shot out of this gun thing, and then they fly towards this pole, and then notice that they can sort of move up and down that pole just because the locator that is the goal for the particles is sliding up and down that pole. So other things that are going on in here is that the particles, and those are in blobby mode right now. If we look at their goal weight, right now they have a goal weight of 0.7. But I've actually animated the goal weight in the scene so that at frame 1 it has a value of 0.4, but then at frame 40 it increases to a value of 0.7. What that means is when we hit play, we'll notice that when they start to be emitted from the gun, they're moving really slowly because the goal weight value isn't very high. But then all of a sudden, once we hit frame 40, they speed up because that's when the goal weight value increases and they become attracted to that locator. So if we took a look at, let's say, the QuickTime movie of that, it's a very simple setup. It's just, allows us a lot of control as far as where in the scene those particles go. And then if we look in this movie, there are actually 3 particle objects in here. There's one which is kind of these greenish particles that are only living for about 15 frames or 30 frames right in the gun area, which are just giving these little sort of glowing sparks at the beginning. Then we have this middle particle object, which is actually the laser beam. And that one is the particle object that actually has the locator as its goal. And then in here, that particle object is emitting these particles that are trailing up into the scene. And so I have particles emitting particles, so that when the laser blast kind of gets towards the end of its lifespan, it creates new particles. And then there's actually a 4th particle object, which is these sparks that are coming off of that pole. And I have an emitter parented to the locator, which is the goal, so that when that laser blast hits that locator, that emitter starts emitting some little sparks in there. They're kind of hard to see, but they're in there. And so in this scene, there's a couple other things to address, though. I do have fields on my particles. You can combine fields with particles that have a goal. And so if we take a look at these, you'll notice, and it's actually it was easier to see in the movie file, that there is some turbulence on them, so that they're not moving in completely a straight line. And then also notice that when these particles get near the locator, they don't get completely stuck onto the locator. They actually kind of turbulently move around the locator. Well, their conserve is at 0.5, which will give you a little bit of an oscillation. but I also have it so that their goal weight not only increases at birth by keyframing it, but I also have their goal weight go down when they get towards the end of their lifespan. Well, that's something that you wouldn't be able to do by just animating the goal weight that you see in the channel box. The goal weight value that we have in the channel box is a goal weight that controls all the particles. So if I grab my goal weight in here, and let's say I delete the keys on it, and I set a value of, let's say, 0, and I hit play, what we're going to see is those particles are not going to be attracted to the locator, just because the goal weight is off. But changing that thing in the channel box, the goal weight value, affected all the particles. And now if I enter that to a value of 1, now we're going to see those particles are going to move a lot faster towards the locator. And so our goal weight is clearly working. But what's a useful thing to be able to do is still notice that even though the goal weight is at 1, that I'm still getting this oscillating motion towards the end of their lifespan. That it still seems like that goal weight is going down when they get near the locator. Well, that's because you can set a value or an attribute called goal PP, so that each particle can have its goal weight specified one by one or by writing expressions, so that you can do things like having the goal weight go down over an individual particle's lifespan, or even do things so that maybe each particle has a randomly assigned goal weight value, so that some particles are more attracted to the locator than other ones. And so to show you what I mean by this is if we go back to, let's say, the previous example where we had just the simple emitter in here. And for these particles, what I'm going to do is let's switch them so that they are multi-point mode instead of multi-streak, and let's give them a goal. So I'll select the particles, and first let's actually create a locator. So I'm going to move this locator up here to the left, select the particles, shift select the locator, add it as a goal. Well, if that goal weight has a value of 1 and I hit create, as we know, those particles will just get stuck right onto the locator. And one thing to point out about these particles is we can see that they seem to change color. That's just because I have expressions on their color so that the color is based on how fast they're moving. So the faster they move, the more red they get. But in here, what I'm going to do is take the particles. You know, if I put the goal to 0.5, then we're going to see how they're going to eventually sort of move towards it. Well, let me give a conserve of, let's say, 0.9, so we don't get so much oscillation. And now let's see how we can set goals on a per particle basis. Well, if you select your particles, and I'm going to lower the goal weight to 0.1 right now, just so they move slowly towards that locator. Well, I want to select an individual particle. To do that, you're going to want to go into component mode, and the first button on the status line, you'll see if you right-click on it, has an item called particles. And so I'm going to go in here, and you can see that I can, marquee drag to select particles. So if I select a few of them and go into the component editor, what you're going to see in here, if you go to the particles tab, because you have several tabs, in the particles tab, we just make this a little bit bigger, you'll see that for each particle it's specifying their position, their velocity, their mass, their lifespan, their color, all sorts of different attributes based on all the PP attributes they have. And this column right here, if you look at the name of it, is goal PP. Whenever you add a goal to a particle object, you will automatically get a goal PP attribute for that particle object. And so we will also be able to see that by selecting the particles and going to the attribute editor. If you close all these and go to the per particle array attributes folder, in here you'll see we have goal PP. And so since they already will have goal PP, you are free to write expressions on it or use ramps and all that kind of stuff. So I already had a ramp on that one. I'm going to break the connection. So right now the goal PP is blank, meaning there's nothing there. Well, when that's blank, what that's going to mean is that basically those particles are just going to use the goal weight that you see in the channel box. But the thing that's very important to understand in here as far as the relationship between the goal weight you see in the channel box and the one that you'll see in the component editor is the one in the component editor, you just grab some particles, is multiplied by the one in the channel box. So your goal PP is multiplied by your goal weight. And so since that's true, if you want to rely on your goal PP to determine how your particles behave, it'll be important that you set the goal weight in the channel box to a value of 1. So that right now, if I hit play, these particles have a goal of 1. But what I could then do is select my particle object, go to the attribute editor, go to the per particle array attributes folder, and where it says goal PP, let's write an expression. I'm going to write a creation expression. And so in here, I've got the expression editor open. And what I'm going to write in here is an expression. There's already an expression on these particles that has to do with that color thing I was talking about. But in here, I'm going to grab goal PP equals, and let's say I do this, rand 0.1, comma 1. And let me take this and get this in Notepad so that it's clear as far as what I'm writing in the expression editor. So I'm going to be writing a creation expression. So what this basically means is that when each particle is born, their goal weight or their goal PP attribute will get a random number between 0.1 and 1. This literally means that some particles will be very attracted to the locator and some won't be at all. And so if we go and enter that creation expression and I hit play, what we will now see in here is that some particles are moving very slowly towards the locator while some are moving very quickly towards the locator. Another thing in here to address is that if I go and set, let's say in that creation expression, goal PP equals 1. And let me just go in here and enter that. When I hit play, we'll be back to having those particles locked onto that locator. Well, if I select the particles and assign a field to them, so let's say we give them a turbulence field, and for the turbulence field, I'll give it a value, let's say attenuation 0. I'll lower the frequency and raise the magnitude, let's say to 5,000. Really high magnitude, and I hit play. Notice that those particles are completely ignoring the field because the goal weight is at 1 and the goal PP is at 1. So those particles are locked on. But if I select the particle object and lower the goal weight, let's say to a value of 0.5, and I hit play, we'll see this. Now we'll see that the particles are being affected by that turbulence, but they're also being attracted to the locator. So whenever your goal weight, or rather your goal PP multiplied by your goal weight, whatever value that returns, as long as that's lower than 1, your particles will be able to be affected by fields that are in your scene. So if I put it in, let's say, first let's mellow out that turbulence field. Let's give it a magnitude of 1,000 and hit play. We can see what's going on. Let's animate the phase on the turbulence field. So I'm going to go in here for the turbulence and say that it's phase equals time, and then hit play. And what that basically is going to do is we're going to have a sort of animated turbulence field. Let's go and say that the phase Z equals time times 4, so the turbulence moves faster. And then hit play. And what you'll be able to see is those particles are sort of moving around in there. Let's grab the particle object and set the goal weight to 0.2. Set the goal weight to 0.3. So with a goal of 0.3, they kind of move around that locator. So now what I'm going to do is set the goal weight to 1, select the particle object, go to my goal PP's expression, creation expression, and maybe say that they equal a random value between, let's say, 0.3 and 0.8. So what this is basically going to mean is that we're going to get this. So some particles get locked onto the locator, so we get a very sort of strong core in there, and then other ones in there are just going to move around with the turbulence. I'll lower the turbulence down to, let's say, a value of 500. Or let's increase the frequency on it and increase the magnitude. So hopefully it's kind of, we're going to be doing a lot of this as far as the relationship between goal PP and your goal weight. I could also go in here, grab my particle object, and write something like this on the goal PP. Let's say I go and write if particle ID when it's divided by 2, this is the remainder function. So the remainder of particle ID divided by 2 equals 0. And then I'll say otherwise the goal PP, let's say, equals 0.3. This one will be 0.8. So what this basically means is that if the particles are even numbered as far as their ID, they're going to get a goal PP of 8. If they're odd numbered, they'll get a goal PP of 0.3. So this is an example of having half of the particles in the particle object behave one way and the other half behaving another way using the goal PP. And so I'm going to go in here and copy this, get that into my expression for the particles, and if I now go in here and hit play, we're going to see that. And so some of the particles are just getting very locked onto the locator, so we're getting that little core, that hotspot in there, while the other ones have the low goal weight. So with the goal PP and the goal PO discussed, let's now move on from using these locators, because now we're ready to start talking about using geometry. So the main things at this point that we've talked about is the importance of your conserve attribute, what goal smoothness does, goal weight, goal PP, which you'll have on each particle object. Okay. And then finally, other than using this expression on goal PP, let me do one more thing, is I'm going to get rid of that expression so that now my goal PP is blank again. And my goal weight has a value of 1 in the channel box. Let's say I select the particles, go to their goal PP, and create a ramp. If I do that, now what this means is that over the lifespan of the particles, their goal will change. So that when they are born, they'll have a high lifespan, but then when they get towards the end of their lifespan, the goal weight goes down. And what we'll see in here is, let's say I grab my emitter and keyframe it so that it only emits particles for a few frames. So let's set a key, and then at frame 30, I'll turn off that emitter. So I'm only getting particles for 30 frames. And these particles, if I go to the attribute editor, have a lifespan of 3 seconds. Well, let's make that 5 seconds. And if I now hit play, we'll see that those particles begin their life completely stuck onto that locator. But as time goes by, what you will see is that they're eventually going to get more and more affected by that turbulence. And so that's because the goal PP has a ramp assigned to it, so that their goal goes down. Let's grab these particles and make them easier to see. Let's get them back into multi-streak. And for this turbulence field, settings are fine. Okay. So now let's move on to using some geometry. For geometry, what you can do is use either poly or NURBS. And we'll start with poly and then get into what the advantages are of using NURBS later. So I'm going to make a new scene and we'll begin with a simple poly object. I'm going to create a polysphere. And for the sphere, let me just scale it up a little bit. Let's say we wanted particles to become attracted to a surface. Well, there's a lot of different examples of when this would be useful. If I go and jump out here just to show a couple movies that are examples of this, let's say we look at this one. In here what I have is particles that are being attracted to a sphere, similar to the sphere we have in Maya right now. And notice how those particles are moving around turbulently. And so the particles have a turbulence field assigned, and then their goal weight to the sphere is less than 1. So when particles are attracted to a surface, with polys, they will be attracted to the vertices. And they're going to behave that way with NURBS as well by default, being attracted to the CVs. The only thing is that CVs don't rest on the surface. But there is a way to get particles to actually be attracted completely to the actual surface itself. And so with those two movies shown, we can kind of jump out here to see how this kind of, or how this behaves. I'm going to create an emitter. And so I'm going to create a omni emitter. And what we will see if I put this emitter, let's say, above the sphere and hit play, we're getting some particles. And I'm going to switch these particles so that they're in sphere mode, so they're easier to see. And I'm also going to change their color so that, let's say, they're all blue. So now I've got some blue particles being emitted from an Omni emitter. Well, I want those particles to become attracted to the sphere. So select the particles, shift select the sphere, and go to the particles pull down and go to goal. If I go to the options, remember that we had goal weight and then use transform as goal. Well, let's hit reset. So that use transform as goal is unchecked because I don't want the particles to be attracted to the pivot point of the sphere. I want them to be attracted to the vertices of the sphere. And we already know what goal weight means. So let's just leave the goal weight at the default value of 0.5. Hit create. Let's go back to frame 1 and let's see what happens. And so hopefully this is kind of making sense to you as far as why we're looking or getting this result. Let's say I take the emitter and move it to the center of that sphere. So it's roughly centered. And we hit play. What we are seeing is that the particles are being attracted to the vertices, but the way that they are being attracted to the vertices is important to point out. The first particle that's born is being attracted to the first vertex. And what you will see is if you right click on your poly object and click on one of the vertices or select a few of them, if you go into the channel box and show the vertices, you will see that they are numbered. Each vertex has a number. So vertex number 237 is going to get particle number 237, or the 237th particle that's born. And that's why we're getting this result where it seems like the particles are rising up that sphere. So for these particles, if I selected them and let's say lowered their lifespan so that maybe these particles only live 1 second and hit play, we're going to see that they're not making it all the way up to the top. Let's say we get them to live 3 seconds. And then they're going to make it up to the top but then die before the next round comes in. Let's say I went in here and put the lifespan, let's say to a value of 10. Then I select the emitter and keyframe it. So for the emitter, let's say it emits particles. I'm going to use stepped keys for just, let's say, about 110 frames. And I'll set that to 0 and hit key. Now when I hit play, we'll see this. Okay. That sphere basically becomes created out of particles, but once we hit frame 110, the particles will stick around. You'll see it didn't actually get to the top few vertices. I would have had to leave the emitter on a little longer. But the point is that we can see how this is growing. Now if I selected these particles, that oscillating motion that we're getting is because of the fact that their goal weight has a value of 0.5 and their conserve is on. If I enter a goal weight of 1, we're going to see this. In the sense that these particles are just going to literally snap onto those vertices. If I enter a goal weight of 0.5 and then lower the conserve, so that we don't, what's going to happen is we're just not going to get quite so much of the oscillating. They're just going to sort of slowly move into the location of those CVs. So if I went in here and let's say left the conserve at a value of 1, and right now the goal weight is at 0.5, we get the oscillating motion, but then maybe I'll select the particles and assign a turbulence field to them. And for the turbulence field, I'm going to turn off the attenuation, and I'm going to write an expression so that the phase Z is animated. So we get a moving turbulence field. And then for that turbulence field, let's hit play, and let's start increasing its magnitude. Let's maybe put the magnitude to 100. So now what we're looking at is turbulent particles that are becoming attracted to the sphere. And so their goal weight is less than 1, so they do move to where the vertices are, but at the same time, since their goal weight is not at 1, they're able to be affected or influenced by a field. If I wanted these particles, let's say to, assume the shape of that sphere faster, I would just have to go in here and have the emitter emit particles faster. Okay. And if I then at some point want the, let's say, sphere to be built out of particles and then the particles to blow away, you would just animate the goal weight. So it's really a balancing act of all these different forces. One of the most convenient or useful tips in here, as far as figuring out how to get the right number of particles for the number of vertices that your object has, is that with poly objects, you can go to Display, Heads Up Display, and go to Poly Count. And in the upper left corner, it's going to tell you how many vertices are in your scene. And if I select this sphere, it'll show me in the second column how many vertices there are in the selected object. So I can see that this sphere has 382 vertices. Well, what that means is I need my emitter to create 382 particles. The way that I can do that, there's a couple ways. Is one, I could set the rate of the emitter to 382 and have it emit particles for 30 frames. Or what I could do, which is what I tend to do, it can be very convenient, is select the particle object. And in here you'll see that if I close all these folders, there is a folder for the particle object called emission attributes. And there's an attribute in there called max count. You're actually allowed in Maya to specify for each particle object the upper limit of how many particles that can have. If I set that to a value of 382, that particle object will only be allowed to have 382 particles. Even if my emitter's rate is set to 10,000, it still will only be able to have that amount. So if I go in here now, select my emitter, I can actually delete the keys on its rate, set the rate to 10,000, and if I hit play, we'll see this. Notice that in one frame, all the particles for that sphere pop up, but we don't get any more than we need. If I select my particle object and go back to the attribute editor, what we will see is if we go to the General Control Attributes folder, if we look to where it says count, we can see that we have the right number of particles. And so that our max count and our count match each other. So that even though again, the rate of the emitter is higher than the number of particles we need, you can limit it by using or create a ceiling by setting the max count attribute. The only thing to watch out for is if any of these particles die, a new one will be created by the emitter. So if you don't want any new ones to be created, you would want to go in and keyframe the rate. So let's say we grab that emitter, go to frame 1, stepped keys, we'll keyframe the rate at 10,000, but then at frame, let's say 10, we'll key it down to a value of 0, set a key. When we play it back, we're going to get the exact same result. But the thing is that I know if any of my particles die, new ones won't be created. So what I could do in here now is select this particle object. And let's say in the beginning we don't want that, oscillating back and forth motion. Well, what I could do is set the goal weight to 1 and hit play, and we'll see this. So that maybe I will go in and keyframe my goal weight, set a key, hit play, particles appear. Then maybe I want them to slowly become turbulent. Well, maybe at frame 40, I will keyframe the goal weight again. And then at frame, let's say 100, I'll have it fade down to a value of 0.5 and set a key and hit play, and we'll see this. And now we have this turbulent behavior. Then if I wanted these particles at some point to just get blown away, I could simply go in and lower that goal weight to a value of 0. So then maybe in here I'll go at frame 200, I'll key the goal weight again, and then at frame 220, I'll give it a value of 0 and set a key. One thing that we're going to have to watch out for, though, is we're probably going to have to keyframe our turbulence's intensity as well, though. Because as those particles become turbulent, we have to put a very high turbulence setting, a magnitude of 100 on the turbulence field, to get those particles to have this level of turbulence. But once their goal weight completely turns off, that turbulence's magnitude will need to get lowered as well, because what we're going to see right now if I play through this is once the goal weight goes to 0, they're really going to fly away really quickly. So let's let this play itself out. And so if you want them to dissipate or disperse more slowly, it would just be a matter of mellowing out the turbulence field or keyframing that at the same rate. And if I want these particles to fade off at some point or fade on, it's just regular opacity PP stuff. I can go into the opacity, add a per particle attribute. And that's going to give these particles a lifespan. So let's say I want these particles to live 10 seconds. So right now my lifespan is set to 10 seconds. And then the opacity PP, I'll just go in and create a ramp. So that maybe these particles will fade on, stay opaque for a long time, and then fade off towards the end of their lifespan. And so now if I go in here at play, we'll see how that sphere of particles just sort of materializes. And then as we play it, we'll see the turbulence will come in. It'll start to behave turbulently. And then they're going to fly away. And as they're flying away, they're going to fade off. And so we can see there how they dissipated. And then let's say in here we want to start doing a few things that are a little bit more snazzy. Now right now we have these particles that are in sphere mode. They obviously don't have to be. One thing that I could do, which is pretty common, is I'm using a sphere, but maybe the sphere isn't necessarily something I want to render. I'm only using it to design my particle behavior in my scene. I could go in here and I'll just get that sphere to be transparent. So I'll create a new Lambert shader for my sphere that I will assign to it and give that a transparency of 1 so that now I don't see my sphere. And for the sphere, I would also go into its attribute editor, go to the render stats folder, and uncheck cast shadows, receives shadows, and primary visibility. So the sphere does not render. I would just render the particles. So now when I hit play, we get this, as far as this fading on. And for these particles, they're in sphere mode, but of course they could be in any mode that I want. I could switch these, let's say, to multi-point. And then for the multi-point particles, I'll go in here and maybe increase their radius. And then for these multi-point particles, I'm going to increase the count, the radius. Maybe I'm going to go to their opacity and edit it so that they never actually have a value of 1. They're never completely opaque. And then also for these particles, I'm going to give them a color, but a per particle color. So I'm going to give them an RGB PP, and I'll write a expression for that. So I'll just do a simple rand function expression. So the RGB PP equals, and let me grab one from my shelf. And so the expression that I just put on the color for those particles is simply that. So that the particle shape 1.RGB PP equals this rand between this min vector and this max vector. So now if I enter that, when we hit play, we'll see that the particles are all kind of bluish. And then for them, we could go in and start playing, as this is even playing back with the multi-count, multi-radius, and so forth. So that we can see that we get this, sphere of particles that appears, becomes turbulent, and then eventually gets blown away. So we didn't have to be using a sphere. Obviously, we could be using a poly object that represents anything from an airplane to a character's face to an entire character's body. Doesn't matter. It really gives you an idea of the power of using this stuff and the fact that something we haven't done yet, and maybe we'll switch this to multi-streak and get things to be a little bit more dynamic once these particles start to move. Let's increase their tail size. And let's lower that down a little bit so we can see how they're moving with that turbulence and then eventually dissipate out into the scene. One thing that we haven't seen is having the geometry that we are using be animated itself. If the geometry or the target goal geometry is animated in any way, including any deformations, meaning that the geometry could be skinned to a skeleton, have clusters, lattices, it could be a soft body itself, the particles will respect that. So what I'm going to do now in here is let's look at that sphere. We can see our sphere is still in here. And maybe I'll put a lattice on it. So I'm going to go into animation mode and create a lattice around that sphere. And then for this lattice, what I'm going to do is, let's say I'll set some keys on some of the lattice points themselves. Or maybe I won't key it. Let's say first I'll just shrink it down. When I hit play, what we will see in here is that our particles are now matching that new shape. And then again, they will be blown away. So that if I actually had animation or keys on those lattice points, so let's say I go in here and set a keyframe, and then I scale those out and set another key, and then scale them in and set another key, and out and another key, and whatever. I'm just setting a few keys so that we have this kind of pulsating result on there. I can go and hide the deformer so I don't actually have to look at it, and then hit play, and we're going to see this. So we'll see that how the streak mode, the velocity of the particles, is actually being influenced by the movement of the vertices that they are seeing as a goal. So notice that they're actually streaking in the direction that the vertices are moving. So let's take a look at that again. And let this play itself out. And then finally, they dissipate. And just so we can see this in real time, we can just go and play blast this in. So I'm just going to make a change real quick to the res that's going to play blast it in. So while this is loading in, things to point out again is if you're trying to create a particle object that looks like a piece of geometry, again being a character, an object, whatever, it's a good idea to have the same number of particles as the number of vertices. And so the way to do that again is to just set the rate on your emitter really high, like a value of 10,000 or 100,000, whatever. And then just have that emitter's rate be on for a few frames. It could be 3 frames, 4 frames, doesn't matter. And then for your particle object, you will want to go in and set the max count attribute to be equal to the number of vertices that that poly object has. And that way you know that when you those particles are created, you'll get 1 particle for every vertex. And the same thing would hold true for using a NURBS piece of geometry as opposed to being poly. So this is just going to load into fcheck, and we can see what we just created as far as this sphere of particles. And so now for the that movie file that I showed in the beginning, before we started talking about this geometry stuff, it should be kind of clear how something like that was done. So getting that back up, what I'm referring to is this one, where I just have this sphere, which has some noise on it for those vertices. Now another thing, or another couple examples that can be useful, is let's say you need to do something where you have a object which is covered in dust, or a object covered in sand, or an object made out of sand. Let's say you have a sand castle that needs to be blown away. A way that you can do that is use goals, model your sand castle out of geometry and polygeometry, get particles onto those vertices, and then you want to figure out, well, how can you get those particles to eventually be blown away, but have a lot of control over how they're blown away. Because in here what we basically have is all of the particles are getting blown away at the exact same time. But maybe you want to do something so that the particles at the top get blown away first, and the ones at the bottom get blown away next. If I look at, let's say we grab a movie file that's an example of that. Let me find that real quick. And that would be this goo one. Here we go. What we are looking at is particles, blobby particles, that are attracted to a surface. And let me make this a little bit bigger. Okay. And then what happens is, notice that those blobby particles get blown off. But notice how the ones at the top get blown off first, and then that kind of gradually moves down. So this can be anything from, dust on the surface to snow, whatever. A way something like this can be done is by having a lot of control over the goal PP, by using things like expressions related to other objects in the scene. When you're referring to particles, you can refer to their position in the scene. So if I wrote something like this, I'm going to create a new variable. So let's say float and I call this whatever. We'll call it position actually. So we're going to create a attribute called position, which equals particle shape 1 dot position. And that's actually not going to be a float, it's going to be a vector. And going down a couple, I can then do things like this. If particle shape, or rather if position dot y is greater than 10, particle shape 1 dot goal pp equals, let's say, 0, else particle shape 1 dot goal pp equals 1. All right, what does this mean? What I've done is written an expression that's querying the position of a particle to determine what its goal weight is. So that this is the case where we're not going to use the goal weight, we're going to rely on goal pp. So in order to refer to the actual position of a particle in y, because what I'm specifically saying here in English is if a particle is higher than a y position of 10 in the scene, so and this particle, if it's moving by a force and a force pushes it above 10, that would also count. So if the position in y of this particle is greater than 10, its goal is 0. Otherwise, its goal is 1. The reason I had to go and do this whole vector attribute thing is that you can't query the x, y, or z position of a particle without doing this. You'd kind of need to. Because every particle in Maya has a position attribute, and that position is a vector. So position is x, y, z. So particle shape 1 position, what you actually would want to query is, let's say, a single component of that vector, like the x component or the y component. So if you create a new variable in Maya, which is a vector, and assign that vector the vector attribute for the position of a particle, you can then go in and say, reference that variable, in this case, which is $ position, and then period x, y, or z to refer to either the x, y, or z component of that vector. And so it's a little weird, but hopefully just by looking at that enough times, you can get that sunk into your head. Because once you're familiar or comfortable with it, it's very, very useful for a variety of types of effects based on what we're talking about here. So let's say I go in back to Maya, and we want to do something where these particles, let's say, become influenced by the turbulence, but it's the ones at the top that do so first. Well, what I would do is select the particles and get rid of the animation I did on their goal weight. So I'm going to delete the goal weight animation and set the goal weight to a value of 1. What will happen now is I get this. The particles are attracted to the vertices, but the thing is that they are no longer going to be affected by the turbulence and blow away. If I want these particles to get blown away, but starting at the top, moving down, first maybe I'll grab the particles, and instead of using a turbulence field, maybe we'll use a uniform field. I'll grab the particles, give them a uniform field that's going to blow them to the right. So let's say uniform field, and the uniform field will be going in the x direction with 0 attenuation, and a magnitude, let's say, of 10. All right. Then what I'm going to do is to get these particles to lose their influence to their goal based on their height. I'm going to reference that by maybe having each particle's goal pp reference the height of a locator. So I could go and say that, if the particle's position in y is higher than the position of this locator, their goal pp goes down. And that way I could just animate this locator moving down to get these particles to get blown away. So I'm going to go in here and actually set some keys on that locator. So let's say I call that locator goal control. So I've renamed my locator. Now it is now called goal _ control. And I will set a keyframe on it so that, let's say, I'll set some spline keys so that maybe at frame 120 it begins to move down. And let's say it takes it 2 seconds to do that. So at frame 180, I've lowered it down. And then I'll just get that to continue to move down in the scene. Let's say to -1000. And I'll keyframe that. So that now if I hit play, what we're going to see is that at frame 120, that locator is going to begin to move down. Then what I need to do is get the goal PP on my particles to query the Y position of that locator. And so to do that, I will select my particles, go to their goal PP, and write a creation, or rather not a creation expression, a runtime expression. Because remember, a creation expression is only calculated at birth, and a runtime expression is calculated every frame. So the expression that I'm going to write in here, going back to Notepad, is my particle is called particle 1, so particle shape 1. So the expression is going to read, instead of having position.y be greater than 10, I'll have it be greater than goal control.ty. So if the position of the particle in y is greater than the y position of the locator, the goal PP is 0. Otherwise, the goal PP is 1. I could have it otherwise have, a goal of 0.7 so that they could still, be acting in a turbulent way. It depends on the kind of effect that you're trying to do. And another thing that can be handy sometimes if this doesn't calculate the way you'd expect is to, instead of saying vector position equals particle shape 1.position, we can query world position so that it's the actual position in world space. And so let's go and copy this and paste this into our expression editor. Enter that expression and see what happens when we hit play. And so at that point, those particles flared out more just because of the uniform field that's in there as their goal rises. And then at frame 120, the locator is going to start moving down. And there you go. And then they're just going to keep moving to the right. And that gives you an idea of how this one was done. The only difference is that instead of using, streak mode particles, this is using blobby particles. But it's basically the same idea. And one other thing to point out is notice that these blobby particles, when they slide off that sphere, slide off of it, they don't go through it. You are allowed to have a goal piece of geometry also be a collision object, so that they can actually collide and slide along that object as their goal weight goes down. So moving back out here, let's go in and play blast this one. So those particles come in, get attracted to the sphere is animated. At this point they have a goal of 1, so they're just doing exactly what that sphere is doing. They don't have any turbulence on them or anything like that. Although actually they might, because I think the goal is actually at 0.7 right now. I think in the expression I didn't, for the else statement, it said equals 0.7, not 1, so that we could have some turbulence. And then now that locator moves down, so you can see as it moved down, how those particles began to speed up. So we can see that the ones at the top of the sphere moved first, and then the ones at the bottom moved later. So there's a lot of different ways you could do something like this. You don't have to necessarily use a locator or write the expression the way I did, but that's typical of mine. There's always more than one way to do something. But hopefully this made sense as far as being a very powerful use of expressions and goals. And now that's loaded in, so I'll just play back a little bit faster. So next thing we want to do is bring up some issues of other things that you might want to do with these particles. And we could actually take a look at a couple other examples first using polygeometry before we move on to NURBS. Let me make a new scene. If I open up, let's say, I'm going to grab this one. Let's take a look at a movie first. The movie I'm going to open up is basically a character made out of particles, this little blobby guy. And in this scene, what we have is I have a character made out of polygons, and then that character is walking through the scene. At frame 0, the goal on these particles is 0. It rises, they become attracted to the walking character, and then at this point, when that raises back up, notice that the particles at the top become affected by a vortex field and turbulence. Well, that's because I'm doing that locator thing again. as this locator is moving through the scene, I can control at what point those particles get blown away. And then they fade off. So same thing is going for this one, where instead of having blobbies, I chose to use a different render method for the particles, so that we can see that kid model, which is just walking around. So whether it's a character made out of smoke or water or dust, or it's very, very flexible. And by having multiple goals, in this case these particles just have one goal, which is that character geometry. But if you needed let's say a character made out of liquid that has the shape of, let's say, one character but then morphs into the shape of a car, you could do that by using multiple goals, like we saw in the beginning with the locators, where we had two locators and the particles were able to move from one locator to the other. You could do the same thing in here by having multiple poly geometry, or it doesn't have to be poly. One goal could be poly and one goal could be NURBS. So to take a look at these scenes that these were created from, let me open one of them up. Let's grab, let's say, this, so we can see some of the issues in the scene. The first thing to point out is that the geometry for the character, I'm going to see what we have visible right now. If I hit play, we're going to see that our particles are not in this scene. But what I will want to do is first, we'll open up the scene with the particles in a sec, but let me first just get the geometry that is the goal to appear. And let's also make a couple changes so that our playback is a little bit faster. So this is the animation that we have. And so we can see that it's about 150 frames of the character walking forward. And I wanted to get this character to be made out of particles. So what I have looking or visible right now is my low-res character, so the playback is fast. But I also have this, which is actually the wrap deformer for my high-res character, because the high-res character in this case is actually sub-D as far as my geometry goes, but we don't even care about that. And you can't use sub-D as a goal anyway, you need to use polys. And notice that in this case I have multiple poly objects. I did that for more of the reason of the way wrap deformers work. I could have used one poly object as far as the particle stuff. But by having multiple pieces of geometry as the goals for the particles, that allowed me to actually use multiple particle objects so that I have more flexibility over the look. Because you'll see that if we go back to that movie file where he was sort of being rendered in a blobby mode, what we saw in that one was that I was able to control different radiuses for the blobbies. So that, notice when we play this back, that if we get his hands, that his hands have a smaller radius for the blobbies than the rest of his body does, because they're different particle objects that actually have different goals. So going back into Maya, I have several particle objects. So what I had to do is basically select the head. I can see in my heads up display that the head has 872 vertices, so that if I select the particle object that gets attracted to the head, we can see that I have its max count set to 872. And then the same goes for all these other particle objects that are in here. But something that's an important point to also make out is that if I take a look at the geometry in here, very often when you model something, like the case for this, notice that the distribution of my vertices is not even, meaning that I have more vertices in the face region than I do at the back of the head. If you need an even distribution of particles, you would not want to use polygons. So that's one of the disadvantages of polys, is that based on the way you model, it might not be even. Now you could always rebuild the geometry so that you do have a more even distribution of vertices. That's really up to you as far as which method you want to use. But we'll see with NURBS later on, we will have the ability to even out the distribution over the surface. So let's go and open a file where we can get the particles to appear. So give this a couple seconds to load in. And this is the one with the blobbies. So if I get rid of my resolution gate and hit play, we can see there are those particles. They come into the scene. and then we can see that they form the character. And so at this point for those particles, we now have Blobby Man walking in the scene. If I select the particle objects, we'll be able to see that they do have their goal weight animated. And so at frame, if I go back to frame 1, the goal weight is at 0.5. And then at frame 30, it goes up to a value of 1. And that's what explains how they sort of begin not being attracted to the kid model and then eventually do become attracted to it. Also for the particles, if I go to the attribute editor and go to their goal PP, I'll be able to see that I have expressions in here. And so for the goal PP, we have a similar expression to what we were looking at before with that sphere. So if I go and copy this and we go to Notepad, the expression I have in this scene is like what we had before, where the position is based on a locator called goal control, same kind of stuff. And so by combining our goal PP with our goal weight, I'm able to control, getting the particles to become gradually attracted to the character and then get relatively locked on. But right now they have a goal of 0.7 as the character's walking, so that I can have a turbulence field that's in the scene so that we get a turbulent behavior on those particles. And if we take a look at that movie file, let's say we do the one, let's say this one, notice that as the kid's walking, there's turbulent behavior in those particles. And so that's because the goal is at 0.5 or 0.7. Same thing in here. Those blobbies are kind of oscillating and moving around in a turbulent way. Let's see. I think that's pretty much the basics in there. Another example with that is, let me open up this one, where instead of using an entire body, I'm using a face. Because if you think of, let's say, something like the movie The Mummy, where there's like that dust storm that has the face appear made out of smoke and dust, that's something that you can obviously do in this way, where you could actually have a model of a face that is skinned to geometry or to a skeleton that has blend shape on it for facial animation, and then you just replace that with particles. So we can see that I have this face in here, and if I actually first we hide the particles, we only look at the animation on the face. I'm going to switch in here, let's say, so that we get better performance. So let's go to real time. And with this visible, if I hit play, we'll be able to see, that we have some motion on this face. It's yawning, it's furrowing the brow. And let's actually make things a little bit brighter. Okay. So the head's moving, furrowing, blinking, opening the mouth. Well, if we select the head, we'll see it's a poly object. And so if I want to then get the particles to be visible, I'm going to hide the geometry, get my particle object to be visible, and then hit play. Just get my playback speed back to play every frame. And then we can see these particles come into the scene. They're born with a low goal weight, and then their goal weight increases, and now we can see that we have this result. And then we'll see that when the model opens his mouth, that is going to become visible within these particles as far as the mouth opening. Again, I have a particle object where its color is changing based on its speed, which is why we're seeing those color variations. But either way, we can see that the blend shape, as well as the clusters and deformers on that face geometry, is being respected by the particles that are moving with it. And so I can get my geometry back on, and let's go in here and say show polys, so that we can see both of these at the same time. So I believe I have a movie that shows this, maybe. Actually, I think that's what this is. It's just basically a play blast of what we're looking at, just so it plays back a little faster. So anyway, that's the basics of using polys. For NURBS geometry, I'm going to create a sphere. And with this NURBS sphere, it's got, at this point, I've got the attribute editor, 4 spans in U and 4 spans in V. And so if I turn on the CVs, we'll be able to see that the vertices do not rest on the surface, which is typical of NURBS. So when we had a poly object as our goal, we knew that the particles would get attracted to exactly where the surface is. So with NURBS, that could be seen as a drawback. But the thing is that the big advantage of NURBS is that you actually can get the particles to be attracted to the surface. You just have to use a couple attributes that are not enabled by default on the particles that are attracted to it. And then also you will have control for how the particles are attracted to the u and v coordinate space of the surface, so that you can actually use creation expressions or runtime rules to get the particles to flow along the surface. And so when we look at an example like this one, what we are seeing is a NURBS head where the particles are flowing along the v direction of that surface. And that's one way that you could get a character to sweat. If we look at this example, what we're looking at, again, is particles flowing along the surface, where I just took a plane, got particles to flow along the v direction, and then used the instancer to get an animated spider to be placed at the location of each one of those particles. Another example is this water ball thing, where if I play this one, I've got particles that are flowing along the surface and then eventually lose their attraction to the surface so they can fall with gravity, and then they fall and collide with the ground. And so we'll be using the goal weight as well as goal PP, but we're going to be using a couple attributes we haven't used yet called goal U and goal V, as well as an attribute called goal offset, which we could have used with polys, we just haven't yet. So the first thing I'm going to want to do is create an emitter. And so for the emitter that I'm going to create, it'll be Omni. I'll place it above the sphere. And then in here, when I hit play, we'll get the particles. And so let me just go in to the outliner and switch these particles to sphere mode. So these particles are popping on, but the emitter right now has a speed of 0. So let me increase the speed. And now we can see particles. For those particles to be attracted to the surface, first off, let me just make them a different color. So I'll add a per object attribute. And then now I will select the particles, shift select the surface, and go to goal. Creation dialog box, I'll hit reset. By default, the goal weight's going to be 0.5 and use transform as goal is unchecked. Now when I hit play, we will see this. Like we did with the poly object. So the particles are being attracted to the location of the vertices, and we can see the vertices are not resting on the surface. Also, since the goal weight has a value of 0.5, we're getting the oscillation. If I selected the surface and went to its history node, the Make NURBS Sphere node, and increase the number of sections to 10 and 10, and hit play, what you'll notice is that the particles are actually respecting the construction history of that sphere, as far as where the vertices are and how they become attracted. So what we're going to want to do is, first I'm going to select the particles, and I'm going to increase their goal weight to a value of 1, so that we just get the particles to become locked on to that surface. And so we can see how they just, the first particle goes to the first CV and so forth. So we can see how they sort of build from the bottom pole up. So how can we get these particles to become attracted to the actual location of the surface instead of the location of the vertices? The way you can do that is by selecting the particles, and in the attribute editor, let me just close all of the folders and focus on the per particle array attributes. By default, these particles have goal PP, which we've already used. But if you click the general button under add dynamic attributes and go to the particle tab, you will see that there are 3 attributes in here that have the word goal in them: goal offset, goal U, and goal V. First, let's take a look at goal U and goal V. So I'm going to add goal U, I'm going to add goal V, and so now I can see these 2 attributes popped up in the attribute editor. Well, when these attributes are created, they have a default value of 0. So if I go back to frame 1 now and hit play, it'll seem like the particles are gone, but what you will see is they actually have popped on to the bottom of the sphere. Because since goal U and goal V have a value of 0, our particles are being attracted to the U0, V0 vertex, which is at the bottom or start point of the surface. Which brings up a very important point. Whenever you're using a NURB surface as a goal, and you're going to use goal U and goal V, it is very important that you understand the UV parameterization of this surface. For this sphere, it doesn't really matter so much how many spans it has. Right now it has 10 spans in U and 10 spans in V. What does matter is the min-max range for U and V. And I can see that the min-max ranges are both 0 to 10 for U and V. And right now the particles are going to 0, 0. Sometimes it can be more convenient, or it's always more convenient if your range goes from 0 to 1, as far as using these surfaces as a goal. It can work with 0 to 10, but if you wanted to change the parameter range, just so you know how to do it, you could just select the surface and rebuild it in modeling mode. If I select this NURB sphere and go to Edit NURBS, Rebuild Surface, and in the dialog box I'm going to say Rebuild Type Uniform, Parameter Range 0 to 1. And then I'll check Keep Number of Spans. So all it's going to do when I hit Rebuild is if I go to the Attribute Editor, we'll see for the sphere it now says 0 to 1 instead of 0 to 10. So if I hit play, still have the same thing though. The particles are going to the bottom of the surface. The other thing that you need to know about the surface is which direction is U and which direction is V. So for this sphere, I can see that this vertex right here, it's really hard to see, but this one looks like a U. And so what that tells me is that the vertical direction is the U direction. So that I can select my particle object. And now let's say we start writing expressions for goal U and goal V. If I went in here and modified them by using rand functions, I'm going to go to both of them and write the same expression. What I'm going to do, if we go to Notepad, is write particle shape1 dot goal U equals rand 0, 1. And then I will do the exact same thing for the goal V. So I'll go paste that in here and write a V. Because since I know that my parameter range goes from 0 to 1 for the surface in U and V, if I write this as a creation expression, what that means is that each particle at birth is going to get a random number between 0 and 1 as its goal U and as its goal V, which means they will randomly distribute themselves across the surface. If my parameter range went from 0 to 10, still like it did before, I could just say rand 0, 10. If I only want my particles to cover half the surface in the V direction or the U direction, I could say 0, 0.5. So it's pretty straightforward. So let's copy this and paste this into the expression editor. So I'm going to write a creation expression. And now let's go back to frame 1 and hit play. And there you go. So now you can see these particles as they are born are not going to where the vertices are. They are actually stuck exactly on the surface. And just like with the poly object, this surface can be deforming, it could be animated, it could be skinned to a skeleton, whatever. And we can see that we're now getting this random scattering of particles across the surface. And so it's going to be less of an issue of worrying about if our vertices are evenly spaced, because now it's really based on the parameterization of that surface. And so if we decided that, we only wanted particles to pop on that surface for a couple seconds, that would still just be a matter of keyframing the rate on my emitter. So that's goal U and goal V. So if I went and modified the expression for, let's say, since I know for this surface, again, if we look at the vertices, if we look down at the base, it's telling us that the vertical direction is the U direction. I could go and modify the expression so that it's rand 0, 0.5 for goal U. And if I hit edit and hit play, what you will see is that I am now getting particles only on one side of the surface. If I wanted them on the other side, on the top of the sphere, I would edit the expression so that it would say rand 0.5, 1. And if I now hit edit and hit play, there they are. Now I still have my goal PP attribute, so I could still go in for that attribute, which has a default value of 1, and use a ramp so these particles eventually fade off, get blown off the surface. So if we wanted to do something like that, let's say I take these particles which have a goal PP of 1 right now and give them a uniform field. Well, if I give them a uniform field that's blowing the particles, let's say in the X direction, when I hit play, we're not going to see anything happen because those particles right now have a very high goal weight. But what I'm going to do is then take my emitter, which is emitting the particles, and I'm going to keyframe its rate. So let's say it emits 1,000 particles per second, set a key, and then frame, let's say 19. I'll put the rate down to 0 and set another key. When I now hit play, it only emits particles for 20 frames. Then what I'll do is select these particles, and let's give them a lifespan. Let's say these particles live 5 seconds. Then what I could go and do for these particles is put a ramp on their goal PP. If I put a ramp on the goal PP that looks like this, what this is going to mean is that those particles are going to have a very high goal weight for half of their goal PP, for half of their lifespan. Then that goal weight is going to fade off. And once that goal PP goes down to black, the particles will see that uniform field and get blown. So if I hit play, we're going to see now these particles live 5 seconds, which is 150 frames. So once we get halfway to there, we can see those particles get blown. If I don't want them to go through the sphere, I can select that sphere and make it a collision object. Just go to Particles, Make Collide. And in the options, I'll turn off the resilience and the friction. And then all I need to do is go to my Dynamic Relationships editor, select the particle object, go to Collisions, and select the sphere. And then for my sphere, I might want to go to the GeoConnector node and increase the tessellation for how it tessellates that NURB sphere for collision calculations. And now if I hit play, what we will see is that those particles, once the goal PP goes down to 0 and they get blown to the right, will actually collide with that sphere and get blown around it and slide along the sphere. So the performance has gotten a little slower now because it's having to calculate the collisions for each one of those particles. But if you look, you can see they're starting to get blown to the right. But what we'll want to notice, if I tumble around, is they are not going through the sphere. They're actually sliding along the outside. And so for something like a surface being covered in dust, or being covered in snow or dirt or mud, this is an example of that kind of usefulness. So this example in here was showing particles that are attracted to a surface and then slide along the surface due to that collision. So the next thing in here that we want to see is, let me take these particles and disconnect their collisions from that surface, just so the performance gets speedy again. And then also in here, I'm going to get rid of the uniform field, and I'm going to get their lifespan up to, let's say, 10 seconds, and I'm going to get rid of that ramp on the goal PP, just so my particles are now attracted to the surface again. And for the goal U, I'll get the particles to cover the entire surface. So it's RAND 0,1 again. Another attribute that we should look at is an attribute called goal offset. If I hit the General button under Add Dynamic Attributes and choose Goal Offset, we'll see this attribute appears, and I can write an expression for that. Goal Offset, if I write an expression, let's go to Notepad, so that for my particles, I'm going to say that particle shape1.goal offset equals, goal offset is a vector. If I do this, equals 0, 1, 0, each particle will be 1 unit in y higher than their goals, so then the area on the surface they're supposed to be attracted to. So if I actually take this and enter it, and let's actually put in 5 units and place that into the expression editor and enter that. If I now hit play, we'll see this. So you can see that our particles are now 5 units higher in y. So that's the goal offset. Goal offset is useful to add sort of more of a random positioning of your particles. So if I like the fact that my particles are, positioned across that surface as far as the shape, but I don't want them all to be exactly stuck on the surface, what I can do is, let's say the goal offset equals 0. That means that we're going to get back to this, where the surface is covered in particles. But if I say that the goal offset equals, and I use this frand function, and let me just go back out to Notepad. There's a function called frand, which returns a vector. If I put frand 1, it takes what it does, it creates a sphere with that radius, a radius of 1, or I could put in a value of 5. So in this case, it would take a sphere with a radius of 5, pick a random XYZ coordinate inside that sphere, and then that would be what it would return as a vector. And so if you use this as goal offset, each particle is going to get this random vector assigned to it. So if I put in strand 1, it would mean that each particle will be 1 unit offset from its goal, but in any direction. So, and it's going to be random. So if I now enter this and go out here and hit play, what we'll see now is that the particles are still in the shape of a sphere. There's now just a little bit of offset, so they're not exactly perfectly on the surface anymore. So if I go to my goal offset and say strand 3, now we have a 3-unit offset inside there. And instead of creation expressions, you could write runtime expressions on that to increase that distance for those particles. And so it's just a useful way to, if you wanted to do something like a smoky character, you might not want the particles to have such a rigid shape matching the object that's their goal. So you could use the goal offset to sort of mix it up a little bit and create a little bit more of a sort of a feathered edge on those particles as far as how they match their target geometry. So at this point, now that we've seen goal U, goal V, and goal offset as far as using creation expressions, now let's move on to using runtime expressions. And so I'm going to create a new scene, and now what we'll use is a plane. And so I'm going to create a NURBS plane, and let's grab that. And for the plane, I'm going to increase the number of patches, and I'm also going to tweak its CVs. Because in this case, what I now want to do is I want to be able to get particles to flow along this surface. And so let me just sort of tweak it a little bit. Okay, and I'll turn on wireframe on shaded. So just like with the sphere, those vertices do not rest on the surface. So if I turn this vertices on, we can see that they are off. And for this surface, what I'm also going to want to do is take a look at the attribute editor so I can see what the min-max range is for U and V. And I can see it goes 0 to 1 for U and for V. So the next thing I'm going to do is create an emitter. This emitter is going to be creating some particles. And for the emitter, by default, its speed is at 0. So let me just get its speed up so I can see these particles that are coming out. And once again, I'm going to get them to be spheres. And I'm going to change their color. So let's say per object, and I'll make them, let's say, green. Let's make them blue so they're not so bright. Okay. Got that. Now I want to select the particles, select the surface, add that surface as a goal. I'll use the default options, hit create. Now when I hit play, we're going to see this. These particles are being attracted with oscillation to the vertices because they have conserve and their goal weight has a value of 0.5. If I select these particles and increase their goal weight, let's say to a value of 0.8, then increase them to a value of 1, you can see how now they are locked onto those particle or onto the CVs. If I hit play, you can see how they build up based on for where CV0 is up to the NCV. So for this surface, I'm going to want to turn on the CVs to see where the start point of the surface is. And what I can see is that the lower left corner is the start point. And this vertex looks like a U, and this vertex looks like a V. So now I know that this is the V direction, going this way. Well, I want to get particles to flow along the surface in V while being randomly positioned in U. For example, to do something kind of like those spiders walking across the surface. So for this, I now need to select the particles and then add the goal U and the goal V. So let me just go in here and select them. Go to the Add Dynamic Attributes, click on the General button, click goal U, add, goal V, add. If I now hit play, all the particles will go to CV00, which we can see is right here on that lower corner. So now if I want to sort of randomly have them position themselves along this edge, that is the U direction. So I would go to goal u and write a creation expression. So that particle shape 1 dot goal u equals rand 0, comma 1. Hit create. And now when I hit play, we can see that these particles are positioning themselves randomly along the u edge at birth, but their goal v is 0. And so they all are not moving or positioning themselves in v. If I went to the goal v and wrote the same expression, as we saw before, edit, hit play, they now spread themselves along the surface. But now let's use a runtime expression instead of a creation expression. Let's say I go in here to my goal v and remove the creation expression, but then I write a runtime expression so that my goal v equals the absolute value of the sine of time. And let's get this into Notepad. What this means is the sine of time returns a value that goes from -1 to 1, -1 to 1 as time goes by. Absolute value of that is going to give us the positive. So now we're going to get something from 0 to 1. So if your parameter space for your surface goes from 0 to 1, then this is going to get those particles to flow back and forth across the surface. If your parameter range goes from 0 to 10, I could take this and say times 10. So now let's go in here, hit create, and see what happens. And now we can see we have particles going across the surface using a runtime expression for our goal v. But the thing is that let's say we wanted something more like those spiders, where these particles are flowing along the surface, but they're not all doing it in exactly the same way. Well, that would be a case where I needed to base the particle's position in v on its lifespan and based on its age. And so the easiest way to do that in Maya is using ramps. And so I'll go to the goal v, I'll remove the expression that's on the goal v, but then I'll create a ramp. So I'll right click where it says goal v, I'll create a ramp. If I edit the ramp, we can see that the ramp goes from white to black. The bottom of the ramp is birth, the top of the ramp is death. And so these particles at birth are going to go to a goal v position of white, which is actually going to be the top edge. So they're going to start on the right side of the surface and move to the left. And there you go. So I could go in here, for example, and get these particles to move from one side to the other side and back to the other side, speed up, slow down, whatever, just by tweaking this ramp. So a common question at this point is going to be, well, what determines their speed? What determines how long it takes for them to get from one side of the surface to the other? Well, that is going to be based on their lifespan. These particles have a lifespan of 1 second right now. If I give them a lifespan of 10 seconds, now what you're going to see, if I go back to frame 1 and hit play, is this. The particles are now moving slowly across the surface. And so now you can see how for something like those spiders, or whether it's a herd of buffalo or an army of soldiers or whatever, this is a really powerful technique to control how particles are moving in the scene. Because it doesn't obviously have to be a case where you're doing character stuff. If you needed to do, let's say, a laser blast, the laser blast we did earlier was very simplistic. It was pretty much a straight line. But if you wanted to do something much more dynamic, let's say like in that Batman movie that had Mr. Freeze, that had that freeze gun, that had these big waving sort of tentacle-like laser blasts coming from it, you could do that where you had a very long, thin piece of geometry that was a soft body. That soft body could have turbulence on it, but then the particles could be flowing along that soft body, moving along goal V or goal U. And so you could create much more dynamic looking lasers, for example, whatever. It's really very flexible. So right now they're all moving the exact same speed. If you wanted some to be moving faster than other ones, I can go to the lifespan mode and change it from constant to random range. So if I now say the lifespan is 10 seconds, but lifespan random is also 10, and I go back and I hit play, now what you'll see is some are moving fast and some are moving slow. And so in the instancer node, if I was going to get a character's instance onto those particles, I would just have the speed that the particle is moving determine how fast the geometry that's instance goes through its animation, so that I could have some spiders that are walking fast, some that are walking slowly, and so forth. And you can sort of get the idea in here of this functionality. And right now these particles, let's say we wanted to do some more work with the goal PP. Right now they're all completely attracted to the surface. Well, maybe I want them to be turbulent as they're moving along the surface. For that, I could simply take these particles and lower their goal. If I go to the attribute editor, I could use the goal PP, or I could just go to their goal weight in the channel box and enter a value of, let's say, 0.5. If I do that, when I hit play, we're going to see this initial oscillation at the beginning. Well, I'm going to move the emitter closer to that top edge, so when I hit play, we see this. And then for the particles, you're going to get that back and forth motion up here, but then in here, they're not really turbulent. And so I will then select the particles and apply a turbulence field. So let's say turbulence. I'll turn off the attenuation, increase the max or the magnitude, lower the frequency, and I'll animate the phase. And so phase X equals time, create, and now when I hit play, what we'll see is that I've got very turbulent particles that are moving along that surface. Let me lower the magnitude down to, let's say, 100. Okay, so particles that are behaving with turbulence, but also still respecting a surface that they're flowing along. So if going back to the example of doing instance characters, if you wanted your characters to not run through each other or bump into each other, I could simply have each one of these particles be a radial field with a small max distance. And so that you just create a radial field and use selected as source of field so that each particle becomes a radial field and then once they have a small max distance, it's like creating a force field around each particle. And that would be respected, but only if the goal weight does not have a value of 1. Because when the goal weight has a value of 1, if I enter 1, they completely ignore any fields in the scene. So you just have to balance your goal weight with what you're trying to do. Another example of things you can do by using the goal PP would be, let's say we want these particles to flow along the surface and then fall off, like sweat coming down a character's face that eventually has to fall off the face and fall with gravity and hit the ground. For something like that, the way you would approach it is I'll go to the lifespan. Right now they're living 10 seconds. Well, let's say I'll get it so that they're all moving the same speed. Well, they have a lifespan of 10 seconds, but maybe what I want is for them to flow along the surface in 5 seconds, or let's say in 3 seconds they flow along the surface and then fall off. And so the way that I would do that is I'll set their lifespan, let's say in this case to 6, and then I'm going to go and get rid of that turbulence field. And for the particles, I will connect them to gravity. Now, they're not going to see the gravity right now because their goal weight is 1. But if I take these particles and go to their goal V, first I'll edit the goal V so that this happens, the goal V ramp. What's happening is that they're going from a value of 1 to a value of 0 in half of their lifespan. So when I hit play, they make it to the other side of the surface, but then they all bunch up on this edge. So that what I then want is when they get halfway through their lifespan, I want their goal PP to go down. So I'll select the particles, go to goal PP, and give that a ramp. And for the ramp on goal PP, you'd want it to look like this. So the goal PP is high until it gets about halfway through their lifespan, at which point it fades to 0. And now we're going to see this. Those particles are going to then fall off the surface. Because once they get halfway across, or all the way across the surface, they are halfway through their lifespan, halfway through the ramp, and at that point the goal PP fades off, or fades to 0, so they now see that gravity field. And so I could then, if I wanted to, have another plane inside here, and this plane could be a collision object, and I could get those particles to collide with that surface. So I'll grab the particles, get them to collide with that plane, and we'll just see that, once they fall off that surface, and let me just move this plane to the side a little bit, we're going to see they're going to fall off and then hit that surface and then just move with gravity as it collides. So you could also use it to do waterfalls and things like that. So that's the basics of using goal U and goal V. So if you wanted the particles to be waving, as they're moving down the surface, you could have expressions on the goal u, so that instead of having the same constant goal u value, they could have random goal u values as they move along in v. So you could use a ramp for v, but then for goal u, you could go in and use a runtime expression based on sign, so that they maybe are oscillating or waving. If I go in here and grab, let's say, our emitter, I'm going to lower the rate down so that we don't get too many particles. Well, all these particles have, a constant u position. Well, if I selected the particles, I could go into their goal u. It already has a creation expression, so they're randomly positioned along that u axis. But I could then write a runtime expression on the goal u based on the sine of time. Sine of time is going to go from -1 to 1, but maybe I just want them to have like a 0.1 offset, so I'll multiply that by 0.1, hit create, and so when I hit play, it's a little high. And if you look, you'll see these particles are now waving. They're going sort of right and to the left. If we want to increase how fast they do that, I'll say sine of time times 5, edit. And so now we're going to get a much more noticeable waving motion as they are moving in the u direction. So that's sort of the basic in there. If I wanted to speed it up even more, I could say the sine of frame instead of the sine of time. Hit play, and now it's a much quicker oscillation. And if I want it to be a larger range, I'll multiply it by 0.01 as far as how they're waving. So let me just get that into Notepad so you can see what I just wrote. So here is my runtime expression. And it's important to point out that I used a plus equals, so that my runtime is basically continuing from where the creation expression assigned them a position in u. So my creation expression was that the goal u equaled rand 0, 1. But then my runtime expression says plus equals sine of frame, so that it takes the u position each particle got at birth and then does the oscillation from that position in u. So plus equals. It's the same thing as saying the particle shape 1.goal u equals the value that it had at the last frame plus this value. Going back out here, now we'll be able to see, we've got the oscillation, but then they still fall off the surface. It doesn't change that behavior at all. So let's go and open up a scene where if I grab and I go into here and we look at these spiders, when these open up, we can see it's simply a NURBS plane, and we can see there are those spiders that are crawling along it. And if I select the geometry, let me just get rid of my gate, we can see that it's a NURB surface. If I select the particle object, we can see that I simply have those goal u. The goal v expression is going to be rand 0, 1, and then goal u has a ramp. And so it's a neat looking result that's actually very, very easy to execute just by using goals with NURB surfaces. The last thing that we're going to talk about with goals is creating relationships between particles and particles. What I have in here is, if I bring a fcheck movie in, is basically a particle grid, which is the goal for another particle object, which is being emitted from an omni emitter that's at the top of this sphere. And so I created the grid of particles just using the particle tool. And then that grid of particles has springs on it, as well as a couple fields. It's affected by gravity, and it falls and collides with the sphere and then drapes off of it. And then by having the orange particles be attracted to that particle object, since they are a different particle object, can have a completely different behavior based on their fields and their conserve. So by having particles be attracted to particles, it's kind of like getting an added level of control over the movement of an entire, let's say, a body of particles, where you could have its behavior in one manner be determined by some fields, but then its, let's say, turbulence could not affect the way that they move as a whole because you have two particle objects in there. So if we look out here, we can see that I do have this grid of particles, and if I hit play, underneath it we'll see that there is an emitter. And so since this particle object, the grid, is the goal for the particles that are going to be emitted out of that emitter, we will see the way those particles appear, where particle 1 that coming out of the emitter will go to particle 1 in the particle object that's the goal. And so the particle object, which is the grid at this point, doesn't have any fields affecting it. But the particles that are being attracted to the particles, if we select these, we will see they have a goal weight of 0.5. So that they do move to where the particle grid is, but they can still be affected by a turbulence field, which has an animated phase in z, which is giving us this kind of rippling behavior in that particle mass. But then when the particle grid starts falling with gravity, they all will follow that behavior. And then that particle grid also has springs on it to keep them together. And so we'll see how they fall, hit that surface, but then because of the springs that are on the goal particles, they stay together in a manner that's very reminiscent to the way soft bodies work. It's just we don't have any geometry in there, it's just particles and particle behavior. And so we'll see that because of the gravity and the springs, they're being slowly dragged off that surface. And then we'll see how they just fall off as a large mass. So another example that we'll take a look at is one which creates a sort of nebulous looking aurora type object, which if we play this, we can see that we have particles that again are becoming attracted to particles. If I open up, let's say, a QuickTime movie of this, just so that it play a little bit faster. What I did is I modeled a piece of geometry, I created a sphere, I stretched it out, I did some CV animation on it, then I turned it into a soft body, applied some turbulence to it, and then I took it and set it to be a goal, or I took its particles and set them to be a goal for another particle object that's emitted with a low particle goal weight at the beginning, and then it raises so that they fly towards their appropriate goal PP positions. And so if we want to go and take a look at the scene to see how this is constructed, if I select the geometry, that is the sphere, which we can see has some CV animation on it. We can also see there's turbulence on that sphere because it is a soft body, so it's moving around. But then it's also the goal for a particle object. And the particle object that's being attracted to the particles of that sphere has one of those, its colors changing based on its speed. So we're getting sort of interesting flare-ups in areas where the goal particles are moving a little bit faster due to the turbulence that is on them. So in this kind of example, you either could, it depends what you're trying to do, it could be an effect where we need the geometry to render, where we could be doing some sort of, a meteor that's surrounded by some sort of gaseous material, or at the same time we could just hide that sphere and then just work with the particle object. So for creating things, like an aurora or nebula, by being able to just go and model a piece of geometry that matches the shape that you need, and then know that that thing can act in kind of a organic way by turning it into a soft body, is very flexible, because then you get to use modeling tools to design a particle object instead of relying purely on fields. So that's all the time we really have to talk about particles being attracted to particles, but all of the same rules apply that we've used for when we had geometry that we're using. The only difference is that we have some unique things we can do, like in the example that we looked at before this, where you can kind of get double field behavior. So that by linking fields to the different particle objects that are different goals, you could go and create multiple levels, so that you could have, one particle that is the goal for another particle, and then that second particle object could be the goal for a third particle object, and you could get interesting trailing effects. So there you go, that's particle goals, and that's where we're going to have to stop.
We hope this DVD has helped you learn more about Maya, and we appreciate your support. Visit thenormanworkshop.com or visit norman3d.com. For training, visit Norman Online. DVDs by Dave Picciuto, Stephen Simon and Alice. Super by Alex Alvarez and Dan Trumley. The Norman Workshop.